All right, so today what we're going to do, let's recap where we were in section 4.1. In 4.1, we introduced the extreme value theorem, which was the basic idea that if you had a continuous function and you had a closed interval, that you were then guaranteed to have a global max and a global min. Now, EVT itself does not find the extreme global min and the global max, but it guarantees that there must be a global max and a global min. So in addition to that, then we kind of extended it and said, well, what if I want to find the global max and global min? Well, Fermat, which is a famous mathematician, and I did put up a reading for you in the It's Learning environment for you to kind of see who he was. He's an interesting character, shall we say, who had a very maybe bad or good habit of pretty much proclaiming that he knew how to do something or knew how to prove something, but would leave out the details. He wasn't one that was big on formally writing up his work. And so he was always challenging other mathematicians to try to come up with what he thought was easily proven. And in fact, if you Google Fermat's last theorem, you'll see something that has stumped mathematicians for over 300 years, which has been more recently proven. Took it 300 years for them to prove what Fermat basically wrote in the margins of a book, that he has a marvelous proof for this that is quite easy, and that took them that long to come up with it. But I did put up some, if you're interested in the historical features of this, some things in the It's Learning environment for you to read. But what we've been doing, I didn't mention this in the last video, but we have been basically using Fermat's theorem, one of them, that said that if a function has a relative extrema at x equal to c, okay, a relative or local extrema, and the derivative exists, then at x equal to c, that's going to be what we call a critical point or value, and it's where the derivative is equal to 0. And in addition to Fermat's theorem, which is giving us these critical values occur where the function has a point and its derivative at that point is 0, we will also have critical values that occur where the function has a point, but yet the derivative is undefined, which is where we're going to have this idea if we're looking for a cusp when we're doing EVT, because if you are continuous, you have a point that exists at x equal to c, but the derivative is undefined, then that would make it a cusp. Okay. Notice we're not in EVT talking about discontinuous functions at all. Those by themselves will have lots of other things that we're going to have to do in order to get extrema, both global and local. And so to find your global extrema, you must first determine that EVT applies, that it's a continuous function on a closed interval, so that you're guaranteed to have them. Once you know you have global maxes and mins, you determine your critical values. And the critical values are values, since we've already determined EVT exists, so these are values where the derivative of that continuous function is 0 or undefined. Then you create a table, and in that table you include the endpoints and the critical values, calculate your y values. The largest y is the max, the smallest is the min. All right? So now coming into our next section, we're going to be going to Rolle's theorem. We're going to start with that. Rolle's theorem is a special case of the MVT. In this section, the kind of like the important theorems that you're going to use on the AP, MVT, mean value theorem, is going to be the one that you invoke from this section. You can say Rolle's theorem if you come across it, and they're fine with that, but you can actually call anything that's Rolle's theorem also the mean value theorem, because Rolle's theorem is a special case of the mean value theorem. We're just going to start with that because it's a little bit easier to understand. An interesting fact about Rolle, even though a lot of the work that he did actually helped take calculus to a new level, the study of the infinitesimals that was going on at the time, he actually was against it. He felt like it was something that was going to lead to fallacies, and he didn't really have a lot of faith in this new calculus that was out there. So it's kind of interesting that he actually has a theorem in calculus named after him, but he was mostly proved this to prove something else in a book that he had written that had nothing to do with calculus. It just had some extensions beyond into the calculus world. So basically, here's the theorem that we're going to be talking about with Rolle. Okay, so we're going to look at a function and notice the same idea that in all of these existence theorems, we're going to have certain conditions that need to be met. So in this case, we're going to have three conditions that are criteria that we need to have before we can invoke this Rolle's theorem. And the three conditions are that we need to have a function that is continuous on the closed interval. And note that I'm going to put a star by this because remember I said in the AP that pretty much if you have no idea which theorem that you are supposed to invoke when you're on a free response question, always start out by showing that the function is continuous on a closed interval, because that actually is a condition in both IVT and in EVT. So, out of your choices, you actually have, some chance of getting a point by going ahead and always proving that a function is continuous on the closed interval. Now, in addition to being continuous on the closed interval, Rolle's theorem has the additional caveat that we want it to also be differentiable. But notice that now that I'm talking about differentiability, I'm talking about differentiability over the open interval. And that might remind you because you cannot be differentiable at endpoints. You might want to remind yourself that it's only differentiable if the derivative approaches the same value from the left and the right of a point, and if I'm at an endpoint, then I do not have a left and a right side, so it's not going to be differentiable at the endpoint. So try to resist the classic mistake of saying that it's continuous on a closed interval and differentiable on a closed interval. You cannot be differentiable on a closed interval. All right? So we're simply looking for differentiability in the open interval. Now, since we have a continuous function already, the only cases that we're trying to rule out are we are trying to rule out cusps, okay, because that would be a place where you're continuous but you do not have a derivative, and it also rules out places where you might have a vertical tangent line as well. Okay, so we're not worried about discontinuities here because we've already proven we have a continuous function, and then we go to the second step, which is now we talk about differentiability on the open interval and make sure there's no cusp or vertical tangents in there. And then the third condition that Rolle's theorem has is that we want to make sure that the y value of one endpoint is the same as the y value of the other endpoint. All right, and then once you meet these conditions, again, this is an existence theorem. So we are basically not finding something, but we are proving the existence of a quantity. And what we're proving the existence of here is that there must be a number in the interval, an x value in the interval, where the derivative is 0. Now, I think the easiest way to explain this is to take a look at just some examples of some functions that meet the criteria. All right, so here I have a function, f of x, and f of x, we're specifically going to be looking on the interval a to b. And I mean, this is clearly, it's just a constant function. So the criteria, is f of x continuous for a to b? Your answer is yes, obvious, it's a straight line. Is f of x differentiable on the open interval a to b? Yes, there's no cusp and no vertical tangents involved in there. And is f of a equal to f of b? And that answer is yes. Both f of a and f of b are in the same location. Okay, and you can go through and in all of these four examples that we're basically looking at can say the same thing. Each of these functions have endpoints that have the same y value, and they are continuous and differentiable in the interval. Same endpoints, same y values for the endpoints, continuous and differentiable in the interval. Same endpoints, continuous and differentiable in the interval. Now, the reason why I picked these as your options is basically once you know that the graph is continuous and differentiable, your options are the graph can travel straight across, it can go up and then come back down, it can go down and come back up, or it may go up and down a few times, but eventually it has to come back to where it started from in terms of this height right here. And if you just think about this, this is almost like an obvious kind of idea, is that if I were to look at the derivative, okay? At points in this interval, like in this is the case. If I were to ask you what f prime of C1 is, what would you tell me? Well, what's the slope of a horizontal line? It's 0, okay? Rolle's theorem, in this case, the slope of every point, if I wanted the slope of C2, that would also equal 0 in this problem. In fact, the slope equals 0 for all x in the open interval a to b in this case. Rolle's theorem doesn't guarantee that. Rolle's theorem guarantees that there has to be at least one. Okay, at least one. There may be more, but there's at least one. Okay, if we look at this option, if the graph starts here, goes up, and then must come back down, and there's no holes or gaps, jumps, or cusp in there, then we are guaranteed that where we turned around to come back down, the derivative at C is going to have to be 0. There has to be a turnaround spot. That's basically all we're saying in Rolle's theorem. We can turn around multiple times. We can have a horizontal slope here, and we can have a horizontal slope here. You can have more than one location, but Rolle's theorem guarantees at least one. And the same thing, if I go down and then come back up, the turning spot that I have has to have a slope of 0. And this is why you have to rule out that there's differentiable, because the idea here is that you want to, a cusp, while it may be a local extrema, is a place where the derivative is undefined. And what Rolle's theorem is saying is that I'm saying that there's somewhere where the derivative is 0. All right. Now, how can we apply Rolle's theorem? If we take a look down here at example 1, this actually goes to the position function. If we think we have a moving object, say a ball that we're going to throw up, and if we have that ball and we're looking at a position function, if the object is in the same place at two different instances, this is where we're doing our f of a equals f of b. Now, we also know, because in this case of where we have objects moving through our world, that the object, when it moves through our world, is going to move in a continuous fashion, because you can't teleport yourself from one spot to another or go through a black hole. So we know that the moving objects in our world are going to be continuous. And we also know that it's going to have to be differentiable as well, because when you're looking at the rate that the object is moving along at, it's not going to have a vertical tangent line, because you have to have some speed. You can't be infinitely fast on this. You may have a very fast point in time where you have a very fast speed, but it's never going to be a vertical tangent line. And then you also don't have a cusp there as well, because you can't magically go from going 10 feet per second to 20 feet per second. You have to move from 10 to 20 feet per second. You have to move through all the speeds in between. You have to accelerate and decelerate, speed up and slow down in a continuous fashion as well. So it's going to be continuous and differentiable. It's kind of a given when we do things like cars traveling, balls being thrown, rockets going up in the air, and then that kind of stuff. All right, so definitely have met the criteria for Rolle's theorem. And so Rolle says that if we are at the same spot at some point in time, so it may be at 5 seconds, I'm 2 feet above the ground, and at 11 seconds, I'm at 2 feet above the ground, then there must have been a time when the speed of the object was 0. Now, whether that object didn't move, which would mean that its speed was 0 the whole time, whether the object was thrown up and had a positive velocity, eventually it would have to turn around and come back down, and when it turns around, its speed would have to be 0. Okay? And then even if you threw something maybe down into water that had some buoyancy and it would come back up, you have to be able to have a place in time where you're at the same spot. So for example, so here we have a video of a person who's going to throw a ball, and we're going to draw our position function over time as he is throwing the ball. So as it starts out, the time is passing, and pretty much nothing happens. And then he starts to throw the ball, and then goes up, and then it comes down. Okay, and then he catches it. So our position function that we're looking at, and I'm just going to move back here a little bit in the video, is that when he's here, he's getting ready to throw the ball, we're at about 5 or 6 seconds. Okay, so I was a little off in my scale here. And then as he throws the ball, the height of the ball will increase up to its max. And then at about, I think it's about 8 seconds. Oop. Try to see if I can get it to pause on where I want it to be. All right, so we'll assume that we're at the top right here. What's happening to his speed? His speed was constant, and then it accelerated. His speed got large, much steeper right here, because he was throwing it up. And then it started to slow down, with the concave coming down, until the speed reaches its max height, or when the position is at its max height, our velocity, our speed that the ball was traveling at, has to slow down, and that speed has to equal 0. All right? So that's our example that we're looking at for throwing example 1. So in this example, just before we move on to the next one, let's make sure that we've shown that we were at the same height. We'll say here at 5 seconds, we're going to set our closed interval to be 5 and 11 when he caught the ball. Okay, so we can set our closed interval to be 5 and 11. Clearly, his position is continuous and smooth, so it's differentiable. So somewhere in the interval, there has to be a point in time where the speed slowed down because the position function went up, and whatever goes up must come down. All right, let's take a look at example 2. In example 2, we're going to determine if Rolle's theorem applies, which means we're checking those 3 conditions. And then the second part of this, part 2, so this is kind of our A, and then our second part, part B, is if it does apply, see if you can actually find it. Okay. Now notice that we're given an open interval here, but if you are going to invoke Rolle's theorem, you must check your conditions as if it were a closed interval to prove that there exists something in an open interval. Okay, so if we look back at the theorem says we have continuous on closed, differentiable on open, same y values, then there's a number in the open interval. So it doesn't bother me that you have an open interval that you are given in the problem, but you're still doing the conditions as if it was closed. So 1, we need to talk about continuity and differentiability. Now, just as a fact that we know that f of x is continuous and differentiable everywhere. And you might think to yourself, why do we know that? What kind of a function is f of x? It's polynomial, because f of x is a polynomial. So that's a fact. And because of this fact, I get to say that f of x is continuous on -2 to 2. Okay? Clearly, if you're continuous everywhere, you would be continuous on the closed interval, and we are allowed to look at continuity on a closed interval because we can have the endpoint and, let's see if I can say this correctly, your left endpoint and the limit as x approaches that left endpoint from the right have to be the same. And then your right endpoint and the limit as x approaches the right endpoint from the left have to be the same so that you have a continuous function. The second condition that we're trying to meet is f of x is differentiable on the open interval. Okay? We know that it's differentiable everywhere, and we know that when we're looking at intervals, you can be differentiable at every point inside the interval. You can't be differentiable at an endpoint because that would be no left side, no right side. But we would be differentiable on the open interval. And then the third one is we need to check f of -2, calculate that, plugged it in, you should get 8. We check f of 2, we plug that in, and we also get 8. So our f of negative 2 is exactly the same as our f of 2. Our endpoints have the same y values. Therefore, Rolle's theorem applies, and what we are going to conclude is there must exist an x value, x equal to c, where c is in the interval, negative 2 to 2, such that f prime of c is equal to 0. There must be a place where the derivative is equal to 0. So that's A. I now know that it exists. Now that I know that it exists, I'm now going to go find it. So to find it, let's take the derivative, f prime of x, 4x cubed minus 2x, and then I'm going to set f prime of x equal to 0. Do some factoring. And I just noticed I have a mistake there. If I take my derivative correctly, 4x and 4x. So I'm going to factor GCF, pull that out, pull out a 4x, we get x squared minus 1 equal to 0. So this occurs at x equal to plus or minus 1 and x equal to 0. Now, when you answer the question, we're trying to find the value, or maybe there may be more than one, values guaranteed by the theorem, which means that they must be in the interval. If you find values that make the derivative equal to 0, do not include them in your answer if they are not the ones guaranteed by the theorem. However, in this case, all three lie in the interval, so we have found 3 different values for which the derivative equals 0. So the values guaranteed by the theorem, which guaranteed at least one existed, we found 3, were x equal to plus or minus 1 and 0. Now, that's Rolle's theorem. Pretty straightforward. Once we're gonna leave that behind now, we're gonna go to the super important mean value theorem. All right, so the mean value theorem, sometimes it's also called Lagrange's mean value theorem, but we're just going to call it MVT for short. So that's what we're going to basically be using. Now, Rolle's theorem is a special case of this, and we'll talk about that in a second. Let's kind of outline the important features of the mean value theorem. Okay. So first, notice that the first conditions or criteria are exactly the same as Rolle's theorem, that you have to be continuous on the closed interval and differentiable on the open. And then the third condition that Rolle's have is that the endpoints are the same. That's why that's a special case of the MVT. Right? Now, once we get these two things, what we do know, and let's kind of take a look, I'm going to kind of talk about this 2 different ways. That it says there exists, so it's an existence theorem, just like we've been looking at with all of these important theorems in calculus, that there exists an x value in the open interval so that its instantaneous rate of change is the same as its average rate of change. And let's talk about this in terms of all the ways that we can think about this. So f prime of c is going to be the instantaneous rate at x equal to c, the instantaneous rate at some x value in the interval, equals the average rate over the whole interval a to b. We can also think of this as the slope of a tangent at x equal to c, some point in the interval, is the same as the slope of the secant through the points, endpoints of the interval a to b. Okay. The average speed at some instant, your instantaneous speed equals your average speed. So let's take a look at this. If we were to, let's think of it with the secant line and tangent line, that if we were to look at the slope of the secant, slope of the secant, that's right here, also known as our average rate of change on the interval A to B. Okay? That somewhere, if the graph, as long as we meet the criteria, that we have a continuous function that is differentiable, no cusps involved. We don't want it to come up and then jarringly come back down, of which you wouldn't even have a slope of a tangent line. We're basically saying if every point in between has a tangent line slope, and every point in between exists, and there's no jumps or gaps or anything like that, then somewhere in the interval we have to have the slope of a tangent line be exactly the same. Okay? There may be more than one place. So we have our continuous function on the closed interval and differentiable on the open. Wherever that secant line slope is, you could have more than one place where it has that same slope. Okay? Just as there exists somewhere that you're going to have. Right? Even if, and now let's talk about Rolle's theorem. Why is Rolle's theorem a special case? If I am talking about Rolle's theorem, then remember we had that additional caveat that in addition to having a continuous function on the interval a to b and a differentiable function on the open interval a to b, that the endpoints were the same. Now let's think about it. If the endpoints are the same, and I am calculating the average rate on the interval a to b, when I do f of b minus f of a over b minus a, we get 0 over b minus a, or 0. So the average rate is 0. So Rolle's theorem basically says there exists a c in the interval where f prime of x equals 0, f prime of c equals 0, and if you think about it, well, that's saying, hey, the slope of the tangent line is the average rate, which happens to be 0. That's why Rolle's theorem is a special case. So usually on the AP, even if it is Rolle's theorem, you can get away with saying either, hey, I'm invoking Rolle's theorem, or hey, I'm going to invoke MVT, because MVT, Rolle's theorem is MVT, mean value theorem. Right? So let's look at example 3. So some examples using this. We're going to determine if the mean value theorem applies to this function on the closed interval 0 to 2. Okay, and then that's A, determine if it applies. And then if we are guaranteed to have a value, then part B is I would like to find it. So let's do part A first. So we have again a polynomial. So f of x is polynomial. So f of x is continuous on 0 to 2 and differentiable on the open interval 0 to 2. Okay? And so that is, we don't have to do anything else, because remember, this is not Rolle's theorem. This is the mean value theorem. So we are done with the conditions. We have met the conditions. So by MVT, the mean value theorem, there must exist an x value equal to c such that the derivative at c is the same as the average rate of change. Okay, and since we know a and b, right, this is our interval a to b. A is 0, b is 2. Yes, I could go f of b minus f of a. I'm going to go f of 2 minus f of 0 all over 2 minus 0, because we are specific to this function. So because we had a polynomial that was continuous in the closed and differentiable in the open, MVT applies. And by the MVT, we are guaranteed to have a value x equal to c where, I should add this in, c is in the open interval 0 to 2 such that its derivative is the same as the average rate of change. That's part A. So part B, they're always going to ask you to find it. So basically, I'm going to take my formula, f prime of c equal to f of 2 minus f of 0, and 2 minus 0, and now I'm just going to calculate it. I need to calculate f of 2, so let's plug that in. 2 cubed minus 2, 8 minus 2 is 6. F of 0 is 0 over 2. I need my derivative at c. So my derivative, I might come up here and just go f prime of x would be 3x squared minus 1. So f prime of c would be 3c squared minus 1. So I'm now going from a formula, plugging in everything I know, and now I simply have to solve for c to find the value that I'm guaranteed. Okay. So move things over. 3c squared equals 4, c squared equals 4/3. And solving for c, you get c equals plus or minus square root of 4/3 plus or minus 2 over the square root of 3, which is, different forms depending on if you're in multiple choice. 2 square root of 3 over 3. Now, I'm going to caution you here. Remember, we're trying to find the value guaranteed by the theorem, which means we're trying to find the value in the interval 0 to 2. So even though there are two values that satisfy this, the one that I was guaranteed by the theorem, the value of c guaranteed by the theorem is c equal to the positive 2 square root of 3 over 3. And you can check that the square root of 4/3 or 2 square root of 3 over 3 is in the interval 0 to 2. Because you're guaranteed to have one, and that's the only one I found that could possibly be in the interval. The negative one clearly is not. All right. So now let's take a look at example 4. Now in example 4, we're permitting a calculator. So let's talk about how we would do this problem on the calculator. First, we want to determine all the numbers that satisfy the conclusion of the mean value theorem. Does the mean value theorem apply? Make sure you should always check that. The answer is going to be yes. F of x is continuous on -1 to 2 and differentiable on -1 to 2. So MVT applies. We are guaranteed to have a value. Okay? What value are we guaranteed? Okay. By the mean value theorem, we are guaranteed an x value equal to c in the interval -1 to 2, such that the instantaneous rate of change at c is the same as the average rate on the interval. So our average rate would be f of 2 minus f of -1 all over 2 minus -1. So that's what we're guaranteed, some value that satisfies this equation. So that's part A. Now we're going to find that. Except we're not going to do this by hand. I know it's a polynomial and you could do it by hand, but we are not going to do it by hand. We're going to show how we're going to use the calculator to do this. Because if you are on the calculator section of the AP, you need to resist trying to find things by hand, and you need to use the calculator to find them. So what we're going to do, okay, is let me clear out what I have here. You are going to need to put into y1 the function that we're going to be looking at. So we have x cubed plus 2x squared minus x. Right? Now down here in y2, this value right here is a number. No, we do not need to calculate it. We're going to let the calculator do this. I'm going to do parentheses. I'm going to go to vars, y vars, choose the function in y1, and I'm going to do y1 of 2. That's like function notation, f of 2, minus, go get your vars for y1 again, and that one we're plugging in negative 1. So you plug that in, close your numerator parentheses, divided by parentheses 2 minus negative 1, and then close your parentheses. Yes, you could do 2 plus 1, yes, you could put 3, but let's just let the calculator do it. Okay. Then we're going to come down, and when we're graphing this, remember we need the derivative. So I'm actually going to turn off the original function, and then remember, how do we graph the derivative? We're going to use the n derived, so we go math, and then we choose number 8. And we're taking the derivative with respect to x of y1, so we go and get that. And to graph, we're not doing a specific one, we want to graph the whole thing, so we put our x in. And so now when I go to graph this, now I could, just do zoom standard or zoom fit and all that stuff, but remember, we're only interested in the values for which we are looking at the negative 1 to 2. So when I do my window, I'm going to do negative 1 to 2 for the x. And maybe let's go by 0.2 here. And then see what I've got and kind of see if I can see the function and see if I have an intersection point, because if I have an intersection point in the window, which I'm guaranteed to have, there must be at least one, then I'm going to use the calculator to find that intersection point. And it does take it a little while to graph, but I can kind of preview here on mine that we definitely, come over here, have a intersection point. So we're going to want to find that intersection point. So we're going to go second, calc. Once it gets there, we're going to choose intersect 5, and you should be on the line and on your derivative, and you can put yourself close to where it should be. Anywhere close is good, and hit enter, and then that will give you the value that we're looking for. Okay, so it has a y value of 4. It's the x value of which we are interested in, because that is the c value that we are guaranteed to have. All right, so to answer the question that we had in this problem, and what do we need to actually write down, because obviously we're not going to import. We already put this in, okay? And so on our calculator, all we basically have to say is this equation is true for c approximately equal to the 0.786. Okay, so c equal to 0.786 is the value in the interval negative 1 to 2, guaranteed by the mean value theorem. So we basically, kind of recapping what we did here, we determined if MVT applies, which guarantees we have one. We write our conclusion from the MVT that our instantaneous rate at C is equal to our average rate over the interval from negative 1 to 2. And then we basically graph the average rate, which is going to be a horizontal line because it's constant. We know it because we know the endpoints of the interval. And we graph our derivative so that we can determine at what value the derivative has the same value as the average rate. Now, just to kind of show you one last thing before we move away, I am going to turn back on the original function now that I know the value of where that occurs. Okay. And then take a look at that graph. Alright, so obviously I paused it so I could go get this and do a couple more and you didn't have to sit there for it. But here we have, this is the original function. Okay, I have taken off the derivative and the horizontal. But basically what I want you to look at here is that if I were to draw the secant line, And let's go for, it's hot pink this time. If I were to draw the secant line between the endpoints and then draw the tangent line at that point, then they are parallel to each other, which means they have the same slope. And that slope, that happens at a value of 0.786. And that's the value that we're looking at right here. Because remember, this is -1 to 2 in my interval. Right? So that's the MVT, and that's also a good summary of using the calculator. Now, example 5 here, we're going to determine if the mean value theorem applies. A, are we guaranteed to have a place where the slope of the tangent is the same as the slope of the secant? And then if it does, find the value of C and work from there. Now, this is going to be a no calculator. Let's take a look at this first one. We have a rational function. We're looking at the interval -3 to 5, and what you should immediately look at is the fact that you have a non-removable discontinuity at x equal to 1. At x equal to 1, there is a vertical asymptote on f of x. So we are not continuous. F of x is not continuous in the interval -3 to 5. Now, don't just jump because you have a rational function and say that MVT doesn't apply, because what if my interval, instead of being -3 to 5, had been, say, -3 to 0? Then MVT would have applied, because that section of the graph for that closed interval, it would have been continuous and differentiable. But here, because x equal to 1 is in the interval of interest where I'm trying to apply MVT, then we're done. MVT fails for this problem. Okay? Over here, let's take a look at that. So now we have x to the 2/3. Okay, and we're looking on -3 to 3. Well, this is always defined. Your domain is -infinity to infinity. It's not discontinuous. So g of x is continuous for -3 to 3. We meet that hurdle. The hurdle that we fail is that g of x is not differentiable at x equal to 0. Now let's talk about how we know that it's not differentiable at x equal to 0. Let's remind ourselves that whenever we have these odd roots, that this is a cusp or vertical tangent alert. Okay, and if we were to take the derivative, g prime of x would be 2/3 x to the -2/3, x to the -1/3. I said something and I wrote the right thing. That this derivative, 2/3 cube root of x, g prime of x is undefined when x equals 0. So it's not differentiable at x equal to 0. And yes, that is in the interval of interest. So therefore, MVT fails here as well. All right, now let's take a look at example 6. As you know, we like to have all these word problems that we want to take a look at. So we're going to have this elaborate speed trap set up on a stretch of road. And we have this pumpkin farmer who's very suspicious. And we're sure that he is a chronic speeder, that he always goes above the posted speed limit of 55 miles per hour. Okay, so this is a position function that we're going to be looking at. So the calculus cops are going to try to ticket this transporter of seasonal gourds, that he has a problem, that he speeds too much. And they want to be able to prove that he speeds. So what they're basically going to do, they're going to set themselves up 5 miles apart from each other. And they're going to hide themselves behind some shrubs and things like that. And calculus A, cop A, is going to spot the farmer, and the farmer's going to pass, and he's going to be going 50 miles per hour. So cop A is going to be like, drat, I can't give him a ticket because he's going under the speed limit. All right. Cop A immediately radios cop B 5 miles down the road, okay, where the cop is going to start his timer. And 4 minutes later, cop B clocks the farmer cruising in at 55 miles per hour. So at the beginning of the interval, his speed was 50. At the end of the interval, his speed was 55. But what they want to do is they want to prove that he was speeding on the interval. And the calculus cops do a quick calculation, and don't you love our TI 88.5 calculator, and he's going to issue the speeding ticket. And for what speed, we're going to first say, why did this happen? Is this going to hold up? And what speed would he be ticketing the farmer? Okay, and this is an MVT problem because this is a position function. So let's define ourselves a position function, S equal to f of t, which is going to be the pumpkin farmer's position at time t. Okay, so our pumpkin farmer, and he's going to be moving along a horizontal line. And as he moves along, we are going to record his position at each time. And then once we have this position function, what we will do is we will then calculate his average speed over the entire interval. Oh, let's first figure out if MVT applies. And if it does, we're going to calculate his average speed over the interval. And based on MVT, we know that at some point in the interval, he is guaranteed to have been going that speed. So first off, this is a position function. Position functions are continuous and differentiable. Now, what interval do we want to look at as we are looking at our nice farmer's little position function? Well, in the given information, we have that it was 4 minutes later that took him 4 minutes to make the trip from cop A to cop B. So let's do our continuous on the interval 0 to 4, and then let's go differentiable on the interval 0 to 4. Okay? Now, we might want to make sure that we are careful in figuring out our speed and make sure we pay attention to units, because we're going to be doing miles per hour, and so this is in minutes, so we might want to go ahead and convert this to what fraction of an hour that is. So I might go ahead and divide this by 60 so that I can have my units in hours. So 0 to 4 divided by 60, 1/15 of an hour, and then 0 to 1/15 of an hour. Right? Because we're doing miles per hour. So it's continuous and differentiable, so the mean value theorem applies. All right, so what are we guaranteed? So by the MVT, we are guaranteed that the instantaneous rate at some value c for x, or let's do t since we're doing time, for time, some time equal to c, where c is in this interval, 0 to 1/15, the derivative of f at c has to equal the average rate of change. The average rate for 0 to 1/15. Now you might be like, well, I don't really know what the function is, but we do know what his average rate is because we know how far apart they were, 5 miles apart, and it took him 4 minutes or 1/15 of an hour. So his average rate, so his instantaneous rate at c would equal his average rate, which is going to be your 5 miles per 1/15 of an hour, which works out to be 75 miles per hour. So basically what the cops have proven is that at some time, in the 4 minutes, the farmer must have been going 75 miles per hour. So he was speeding. We don't need to know at what time he was speeding, but we can guarantee that he was speeding. And this actually is kind of interesting because if you take a look, those signs that are out on the highways where they say that your speed is being monitored by an airplane, basically. What they've done in Virginia is what they do is they have basically on the highway, somewhere on the highway, they have a mark going across it. The airplane is going to time you because they can see, or helicopter, by air. The airplane or the helicopter in the state of Virginia, they're going to start the clock when you hit this line. Okay? They are going to stop the clock when you hit this line. So they're going to measure how much time it takes you to travel between the two lines that it sees from above. So you'll never see the cop. They're up above you somewhere, and they're going to calculate this time. And they know how far apart these bars are. So they're basically going to take that distance that they're apart, divide by the time that they clock you at, and that's going to get your average speed. And then they're going to write you a ticket if your average speed is above what the posted speed limit is for that stretch of road. And that's how the getting a speeding ticket by air happens. They basically can radio down to the cop and say, this person was speeding. You may not have been speeding at the instant when you passed the cop, but you were speeding on this interval at some point in time, and they will write you a ticket for that. So that actually is a law in Virginia. So you do want to be careful and be aware of people in the air clocking you on your speeding. All right, let's take a look at example 7. A few more examples of using the MVT. All right, so we have a function that is differentiable for all x. Now this is just a reminder from our section on differentiability that differentiability implies continuity. So there will be problems where you're like, I don't know what the function is, so I can't get both parts of the MVT. If they tell you that the function is differentiable, then you know the function is also continuous. Okay? Now, part A. We're given that we have a function that at 0 is -3. We're also given that the instantaneous rate is smaller than or equal to 5 for all values of x. So we're not going to have an instantaneous rate that goes higher than that. And we want to know how large can f of 2 possibly be. You might be like, well, how in the world am I going to use MVT here? Well, what we're going to do in A is we're going to set our interval. We're going to use this function f of x, and we're going to look at the interval since I have an x value of 0, and I'm interested in f of 2, so I'm going to look at the interval 0 to 2. Now, clearly, since f is differentiable, f is continuous on 0 to 2 and differentiable on 0 to 2. Okay, so we get that. Therefore, so MVT applies. Now what that gives us, we are guaranteed that f prime of some value c for some c in the interval 0 to 2, f prime of c is going to equal the average rate of change, f of 2 minus f of 0 all over 2 minus 0. Now we also know, which was given to us in the problem, that f prime of c has to be less than or equal to 5. Right? Because all values of x have an instantaneous rate less than or equal to 5. Therefore, f prime of c is less than or equal to 5. So by substitution, just basically going to take this and substitute it in. So we know that f of 2 minus f of 0 over 2 has to be less than or equal to 5. So from there, what MVT gives us is an inequality we can solve for f of 2. We're trying to figure out how large f of 2 can be, an inequality. We know f of 0, so we get f of 2 minus f of 0 is -3, so that will be plus 3. Let's multiply both sides by 2. Has to be less than or equal to 10. So f of 2 has to be less than or equal to 7. So we can figure out that f of 2 must be no larger than 7, based on the mean value theorem. Okay, so, and that's basically what we're doing here. It's like, oh, I can recognize, now that we've seen this problem, that if I have a problem like this, then I can use MVT to come up with a formula. I know this, which is what I was given, and then this gives me a formula that I can sub in with an unknown, and I can then solve for the unknown f of 2 and figure out an inequality for that. Okay. Let's take a look at B, which is a very similar type problem. All right, now for part B, let's see where I can fit this in. Now that we know what we're doing, we can kind of shortcut a little bit. So I'll just put B right here. So now we have f of 5 equal to 2. Our instantaneous rate is always greater than or equal to -3 for all x. And I want to find the largest possible value of f of 1. Right? So we're going to set our interval. Since I know f of 5 and I'm interested in f of 1, we're going to look at f of x on the interval from 1 to 5. And we do have continuity 1 to 5 taken care of, and we do have differentiability 1 to 5 taken care of because we knew it was differentiable. All right? So by the MVT, we are guaranteed that f prime of c has to equal f of 5 minus f of 1 over 5 minus 1. All right, we were given f prime of c, f prime of x, for all x values. So that means f prime of c has to be greater than or equal to -3. So again, I'm just going to substitute this value for f prime of c right here into my inequality. So f of 5 minus f of 1 all over 4 has to be greater than or equal to -3, and then we simply solve. F of 5 is 2 minus f of 1 greater than or equal to -12. Subtract 2, so that's -14. And then I'm going to multiply by a negative. F of 1, switch your sign, is less than or equal to 14. So the largest possible value of f of 1 is 14. So the mean value theorem, even though you might not recognize it at the beginning, is exactly what you need in order to determine the largest and smallest value for this type of a problem. All right, now a couple of things that also we kind of get with the MVT. Let's take a look at this theorem, which you already basically know this, is that if I have two derivatives that are equal to each other, if two derivatives are equal, then we basically know that if two functions have the same derivative, that those functions can only differ by a constant. That our f of x has to be the same function as g of x, maybe plus a constant. Okay? So another way of saying this is that f minus g, if I were to subtract them, has to be a constant, because that derivative of a constant is 0. So that's pretty straightforward. So let's take a look at example 8, and that'll wrap up this section here. And you'll kind of see what goes on with this. So we're going to find a function whose derivative is sine of x and whose graph passes through the point 0, 2. Okay? So, and this is a preview of what's coming in the next chapter. We know the derivative is sine of x. So this process, we're going to have to work backwards. We're going to work backwards to f of x. This process that we're going to do in the next chapter is called anti-differentiation. Okay, so this is a preview of coming attractions. Right? Now, you can pretty much, if you just think about this, go, the derivative of what is sine of x? Well, the derivative of cosine is negative sine. So maybe I need to say that the derivative of negative cosine of x is going to be sine of x. But now, really, is this the only function that actually could give you this derivative? Pretty much, negative cosine of x plus 1 would work. Negative cosine of x plus 2. Negative cosine of x plus 3. That basically, we don't know what constant may or may not have been there. So we go plus c. Okay? This anti-differentiation, also called integration, this is going to be called the constant of integration. Now, the only way to know what that value is to actually have information about the original function. Now, this original function passes through the point 0, 2. So what we know is that f of 0 equals 2. Now, this is what we call an initial condition. And this is basically a condition that is going to help us find the constant of integration. So we basically plug that in, f of 0, and f of 0 equals negative cosine of 0 plus c, and that equals 2. So then basically we can use this information to solve for the constant of integration. So cosine of 0 is 0. Oh no, cosine of 0 is 1. I'm almost as bad as you guys. So negative 1 plus c equals 2, and c would equal 3. So the actual original function that we must have had is going to be negative cosine of x plus 3. Okay, so that is the function whose derivative is sine of x that also passed through f of 0 equal to 2. Okay, and so this is kind of giving you this, what's coming down the pike is when we start doing anti-differentiation, not only do you need to know the derivative rules going forwards, you're going to need to know them going backwards. And that's the end of the section 4.2 video.